Alright, let's consider an optical shaft encoder example where we have a motor and we want to know the position of that motor somewhere around the 360 degrees. So we can use an optical shaft encoder for that, where we have a light source projecting through and a photosensor on the other side, and then some sort of encoded disk that we're going to use to indicate where we are around that disk. So let's consider two possibilities, one being the binary code for the positions and the other being gray codes for the positions. This is the table for decimal to a 421 coded binary decimal and the gray code equivalent. The 421 code would be similar to a binary coded decimal, which is how most people are familiar with binary numbers counting up from 000 to 001, 010, whilst the other code is the gray code, which you may not be familiar with, but it was named for Frank Gray, who patented its use for shaft encoders in 1953. The idea of the gray code is that it's a code having the property that only one bit at a time changes between codes during counting. So you'll notice here that as we count up or down in decimal, say between 0 and 1 or 1 and 2, then the code word for the gray code only changes by 1 bit position. So that includes between 7 and back to 0. Whereas the 3-bit binary code changes multiple bits at a time in certain circumstances. Then the question really is, does this special gray code property have any value for us when we're thinking about the shaft encoder? So if we look back carefully at this shaft encoder, we can see that as the light source and sensor is rotated relative to the encoder disk, from the 000 position, we notice that when it transitions between 000 and 001, that first bit could be either a 0 or a 1 when it's on the threshold. There is going to be a point at which enough light gets through that it's ambiguous as to whether it's a high or a low. Now, in this case, because it can either be 000 or 001, it's not really a problem. It means that the angle could only be out by a small fraction. However, as we continue to rotate it around and we get a nice clean reading 001, when the transition goes between 001 and 010, we notice now that there are 2 bits that are ambiguous. So it could be 0, and then the other 2 values could either be 0s or 1s. So therefore, there's 4 possible states there. Could be 000, 001, 010, or 011. Now, out of those 4 states, 2 are reasonable, that is, stepping between the values of 1 and 2. However, the other 2, 000 and 011, are definitely not what it is, and we don't want the encoder to mistakenly think that it's jumped backwards or that it's jumped over one of the segments. This would also be a problem if the system was powered up with the encoder in this state. It may be that if you think you're at 000, you want the wheel to move forwards, when in actual fact, if it was at 010 at 2, then you'd want it to move backwards. And so due to your mistaken encoder reading, you actually move the motor in the wrong direction. So as we continue to rotate it, we get 010, which is fine. Then there's another state transition where there's only 2 possible states, either 010 or 011. And these are also reasonable. And then we come to one of the worst cases, which is where all 3 bits are ambiguous. So we could have any one of the 8 states, because the first bit could be 01, the second bit could be 01, and the third bit could be 0 and 1. This is the worst case, along with another case where you go between 7 and back to 0, and could significantly change the decision you make based upon this encoder reading. As we continue on, we get 100, which is fine. Then another one where there's just one state that's ambiguous. Then the transition between 101 and 110 is ambiguous in 2 bits. So it could be in 4 states, 2 of which are reasonable, 2 of which are not. Another transition between 110 and 111 is just a change in 1 bit. And then the transition between the 7th segment and back to the 0th, where you go between 111 and 000, has all of the bits changing again. And when you're on the edge, you've got the chance of being in any one of the 8 states, which is less than ideal. Gray code, on the other hand, whenever there's a transition, you'll notice that it's only 1 bit that's changing. So between 0 and 1, it's just that first bit that's changing. Between 1 and 2, it's the second bit that's changing. Between 2 and 3, it's the first bit that's changing again, and so on. So as we go around, you'll notice that there's never an ambiguous state where there's a possibility of more than 2 resulting states, even going back between the 7th state and the 0th state. So that is between 1, 0, 0 and 0, 0, 0. So great, we used the gray code for our shaft encoder.